Okay guys, notes for 8.1, Introduction to Vectors. You're going to have to excuse my voice. I'm still pretty hoarse and kind of have a hard time talking, but I know that some of you are really waiting on these videos, so I'm just going to try to push through and hopefully you can understand and my voice will hold out. Okay, so as we start talking about vectors, if you've had a physics class before, you're probably very familiar with vectors. And we're just going to start kind of laying the foundation for terminology and descriptions of vectors. So it says many physical quantities, such as speed, can be completely described by a single real number called a scalar. Okay, this number indicates the magnitude of the quantity. Okay, so as we know, the scalar is a number, and it can represent speed, and it can represent some other things as well. A vector is a quantity that has both magnitude and direction. So two characteristics, magnitude and direction. And we're going to see here in just a few minutes that magnitude can be speed, it can be distance, and it can be force. So first of all, in example 1, we're going to state whether each quantity described is a vector quantity or a scalar quantity. So we're looking for speeds and directions. Example A says a boat traveling 15 miles per hour. This is actually only going to be a scalar. There is no direction on this, just a speed. Okay. Then in example B, we have a hiker walking 25 paces due west. So 25 paces, it's not really a speed, but we know that that is a direction, not a direction, that is a distance, and it does have direction. So this is absolutely a vector. It has distance or length to it, and this has direction. And the last one, a person's weight on a bathroom scale. The person's weight is actually just a number, true. However, the gravity provides direction. It's a force that is pulling against gravity. So we would say that this is a vector. Gravity pulls down. And you may recognize that concept from your physics class if you've had that before. Gravity provides direction in this case. Okay, let's talk about some notation. A vector can be represented geometrically by a directed line segment or arrow diagram that shows both magnitude and direction. I remember in my geometry class we called them rays, right? And you probably still do. They have a starting point and then they go on forever in one direction. So there's two parts to these vectors. If we look at the vector to the right, it has an initial point A right here. And this is also known as the tail. The terminal point, which is at B, is known as the tip. And that's probably familiar as well. We can write the names of these vectors in a couple of different ways. It starts at A and ends at B, so we can use capital A, B with that vector symbol over the top. You can also see it's labeled with a lowercase a, giving title to the whole vector, so we could just have a little a with a vector over the top. Or one of the most popular that we'll see is that lowercase a, but it's bold. So that's probably the most popular. Okay, if a vector has its initial point at the origin, this is what we would call standard position. And that's where we're going to picture most of our vectors coming from. The direction of the directed angle between the vector and the horizontal line that could be used to represent the positive x-axis. So this right here would be that direction angle. The length of the line segment represents and is proportional to the magnitude of the vector. Again, magnitude can represent length. Okay, as we start out and talk about these angles, there are two types of bearings that we're going to use. And keep in mind, these are bearings in application situations, okay? There is a third way that we're going to draw these angles, but first of all, we're going to talk about the two types of bearings. So the first one is quadrant bearing, And it is exactly what we would think. There are 4 quadrants. 1, 2, 3, 4. So a quadrant bearing will never go over 90 degrees because there are not more than 90 degrees in a quadrant. This is going to most often be represented by the Greek letter phi, which is right here. It's a directional measurement between 0 degrees and 90 degrees east or west of the north-south line. The quadrant bearing of a vector that measures 35 degrees below the positive x-axis. So let's draw this over here. 35 degrees below the positive x-axis is right here. But quadrant bearing means how far east or west is this angle of the north-south line. So if we're referring to the north-south line, we're actually going to measure from there. So 90 minus 35 gives me a 55 degree measurement. So this is now, if this is north, east, south, and west, we would say this is from the south line 55 degrees east. And there's a couple of different ways we say that: 55 degrees east of south, or south 55 degrees east. Quadrant bearings are generally used in applications such as with cars, trains, just in general ground navigation. Okay, so let's look at this first example. It says a sailboat leaves a pier and heads due west at 8 knots. Okay, so that's important. It heads due west at 8 knots. Now, knots, 1 knot is 1 nautical mile per hour. That's important to know. So a knot is 1 nautical mile per hour. After 15 minutes, the sailboat tacks, changing course to north 16 degrees west at 10 knots. Find the sailboat's quadrant bearing and distance from the pier after 12 minutes on this course. So this seems like a really intimidating problem, but let's just start to draw the situation. Here's the pier, and the sailboat's going to head due west at 8 knots, but it's only going to do that for 15 minutes. So we want to know how far or how long that's traveling, or how far it's gone. So if there are 8 knots in 60 minutes, then how many knots would there be in 15 minutes? Well, if I do 16 divided by 4, or 60 divided by 4, that's 15. So 8 divided by 4 is 2. So this represents 2 knots going due west. Now it's going to change course. Well, when it changes course, because we're in quadrant bearing, we're going to go from the north-south line. It says that it's going to go 16 degrees west of north. So 16 degrees to the west of the north line would be this way. And there's 16 degrees. So it is west of the north line. And it says that it does this at 10 knots. So find the quadrant bearing from the pier after 12 minutes. Well, if it's now sped up to 10 knots in 60 minutes, then that's how many knots in 12 minutes. So again, if I divide 60 by 5, I get 12. So I would divide 10 by 5, and that's also 2. So I have lengths of 2. Okay, so now that we have it drawn, find the sailboat's quadrant bearing and distance from the pier. So what I'm wanting is this. And I'm going to draw another north-south line, because if they want the quadrant bearing, if I'm standing on the pier, this is the angle in question that I'm wanting. Okay, so if I want magnitude, that's going to be the distance from the pier, so I want to find that opposite side. Well, I know that this is 90 degrees, and 90 plus 16 gives me an angle of 106 degrees. So I'm going to use the law of cosines because I have side, angle, side. So I know that I can take the magnitude squared equal to the side squared plus the other side squared minus 2 times each side times the cosine of 106 degrees. And we want to type that into our calculator, take the square root, and magnitude should be 3.2, which is miles from the pier. So there's my magnitude of 3.2. Okay, so now I want to know the angle measure here. Well, if I stay working inside the triangle, I can use the law of sines. Okay, so now as I look at this angle, I'm going to use the law of sines, and I want to find this angle in here. So as I look for that angle, I can say that the sine of angle P over, let's see, that's over 2, is equal to the sine of 106 over 3.2. And so as I solve for angle P, I get that the sine inverse of 2 times the sine of 106 degrees, all divided by 3.2, is equal to angle P, and that is 37 degrees. So since I know this angle is 37 degrees, to get the bearing angle, I'm going to take 90 minus 37 degrees, and that's going to leave me with 53 degrees, and that is west of north. So my angle will then be 53 degrees west of north, and I know that my magnitude is 3.2 miles. Okay. All right, the other kind of bearing that we're going to talk about is true bearing. This is sometimes called an aeronautical bearing. It is a directional measurement where the angle is measured clockwise from north. That's super important. It is just from the north line and clockwise. Another thing to note is that true bearings are always given using 3 digits. So a direction that measures 25 degrees clockwise from north would be written as a true bearing of 0.25 degrees. True bearings are generally used in applications with airplanes, anything above the ground, aeronautical. So anything moving above ground. Okay, so let's look at this next example. We have a Boeing 777 aircraft. It takes off from O'Hare Airport on runway 2 left. So I have an airport right here. And it takes off with a bearing of north 20 degrees east. So if my bearing line is right here, and the airplane takes off 20 degrees east of north, here is going to be my airplane. And maybe 20 is more like right there. So here is my airplane. Okay, it says, oh, and this is 20. Don't want to forget to label that. After flying for 1 mile, so that's my distance or my magnitude, the pilot requests permission to turn 90 degrees and head towards the northwest. The request is granted and the plane goes 2 miles in that direction. And there we go. So this is 2 miles, and I know that this is 90 degrees. So what aeronautical bearing should the control tower use to locate the aircraft? So from the airport now, we want to look at this vector here. And if I want the bearing, I'm looking right there. But it does say aeronautical bearing. So honestly, I'm going to want to go from the north line all the way around clockwise to right there. But what is going to help me is to get that small angle there on the inside. Okay, so because I have a right triangle, and as I look at this right triangle, I know that I have a 20-degree angle and a little bit more, and then I know I have two sides. So according to the angle that I know some stuff about, I have the opposite and the adjacent. So to find that whole angle, I'm going to take the tangent of theta and set it equal to opposite over adjacent, 2 over 1. And theta is going to be 63.43 degrees. That's the entire angle. So now I'm going to take the 63.43 and subtract the 20-degree bearing, and that gives me 43.43. And that is this little angle in here. So I could say that it was 43.43 degrees west of north, but if they want an aeronautical bearing, I'm going to take 360 degrees and subtract 43.43. And that gives me 316.57 degrees. So the aeronautical bearing all the way around from the north line is 316.57. Okay, so those are the two different kinds of bearings. The next thing we're going to do is probably something that if you were in a physics class you may have done before, where you actually measure the length of vectors to draw them to scale. So we're just going to ballpark these in pre-cal. So let's take a look at this first example. So we're going to sketch a diagram for each quantity listed, including a scale. So we want a scale for like real world or a real life measurement. So vector A we're going to draw, it's 20 feet per second for 5 seconds at a bearing of 0, 30 degrees. So here is my north bearing, and 30 degrees might be maybe about here. Now, when I go to label the magnitude, it says we have a speed of 20 feet per second. So to give this a scale, I'm going to say that 1 centimeter would represent 20 feet of distance. And if I'm going to draw this for 5 seconds, I'm going to let this measure 5 centimeters long. So sometimes we would take a ruler and do that, but we're just going to label and call it 5 centimeters. Okay. Now let's look at the next one. 70 pounds of force at 140 degrees to the horizontal. So if it is to the horizontal, we have this, which is like the positive x-axis. But keep in mind, this is just a vector, not an angle. It is 140 degrees from the horizontal, which would be right here. So my vector goes in this direction. And we want it to represent 75 pounds of force. So if we let it represent that much, I'm going to let 1 inch maybe for my scale be 25 pounds of force. So there's my scale, and then I would be able to make this vector 3 inches long. And again, in a physics class, you may measure that out and literally draw it 3 inches. Okay, letter C. 30 miles per hour for 2 hours at a bearing of south 60 degrees west, and this is vector Z. So I'm going to draw my north-south line, and because this is quadrant bearing, I'll draw my east-west line, and so I have a bearing of south 60 degrees west. So 60 degrees west of south is probably in here. Okay. So 30 miles an hour for 2 hours. Let's let 1 centimeter represent 30 miles. And if we're going to do this for 2 hours, then this would be 2 centimeters long, because it would need to represent 60 miles. Okay, types of vectors. So parallel vectors have the same or opposite direction, but not necessarily the same magnitude. They can be different lengths, different speeds, and have different forces. Now, equivalent vectors would have the same direction and magnitude. Opposite vectors are going to have the same magnitude, but different direction. So the vector opposite A is written like this, negative A. So if we have this vector, A, this vector would be negative A. Okay, and it's important to just restate the magnitude of a vector can represent distance, speed, or force. When a vector represents speed or velocity, the length does not imply distance traveled. Sometimes all we're working on is speed. Okay, so now when we do vector addition, we're going to look at two different ways that we can add vectors together. So we have the triangle method and the parallelogram method. So it says when two or more vectors are added, their sum is a single vector, and it is called the resultant. In some books in physics or in other books, you may hear the displacement resultant. So this vector has the same effect as applying one vector after the other. Geometrically, the resultant vector can be found using either of these two methods, triangle or parallelogram. So if we take a look at the triangle method first, this method is where we would put the tip of one vector to the tail of another vector to find the resultant. So we would actually slide the vectors around so that the tip of A would go to the tail of B. And what's going to happen here is the resultant would be completing the triangle from the tail of the first one to the tip of the second one. So it completes literally the triangle. The other one is called the parallelogram method, and this is where we have two vectors that are tail to tail. So we would slide A and B together so that they are tail to tail, like you see right here. And then we're going to complete the parallelogram that would have A and B as two of the sides. So we draw those dashed lines. Now the resultant is the vector that forms the indicated diagonal. So when you have a tail to tail, the resultant comes from the middle of those two vectors. It comes right up through the middle. Doesn't mean that it bisects it, but it does come in between vectors A and B. So we're going to look at this first example, and we're going to do it both ways. The first way doing the triangle method, and the second way the parallelogram method. So we're going to use the law of sines and cosines to solve this. So that's another reason that 4-7 fits really great onto the beginning of chapter 8. Okay, so we have a vector u with a magnitude of 120 units, and it has a direction of 50 degrees east of north. So we're going to draw that. So here is my north-south and my east-west, and my vector is 50 degrees east of north. It has a magnitude of 120 units and a direction of 50 degrees east of north. Let's label that. And then we have vector v. It has a magnitude of 80 units, and it's parallel to the positive x-axis. So I'm going to start at the tip of this one, and I'm going to draw this next vector. It is 80 units long, and as you can see, it is parallel. So the triangle method says that we are just going to complete the triangle, and that's my resultant vector with a magnitude. Okay, so now what is the magnitude of the resultant vector of u plus v, and what is its quadrant bearing? So if I want the magnitude, I have two sides, but I don't really have any angles inside the triangle. I'm going to blow this up just a little bit. So here's what I know. Oops. So I know that the quadrant bearing is going to be this whole angle right here, which means I'm going to need this little guy, phi. And then once I have phi, I'll add it to 50 and have my quadrant bearing. It's going to be something east of north, but I'm not sure yet. Then I also need the magnitude. Well, to get the magnitude, I have a side, and I have an angle in the middle here, and I have two sides including, or that are on the other, that make up that angle, I should say. So I really would have side, angle, side, and the way that I can figure out that obtuse angle is to know that this angle would be 40, and this angle would then be 140 degrees. If you think about, and I know we're not doing the parallelogram method, but using some geometry knowledge, thinking about that as a parallelogram, it would have to be consecutive angles are supplementary. So it would have to be 140. So, taking those off of there. So now I can use the law of cosines. So I have m squared equal to 120 squared plus 80 squared minus 2 times 80 times 120 times the cosine of 140. So when I find the magnitude and I take the square root of that, I get a magnitude excuse me, of 188. So with a magnitude of 188, I can now find this phi angle inside by using the law of sines. I can take the sine of phi over 80, which is its opposite side, and then I have the sine of 140 over 188. So phi is equal to the sine inverse of 80 times the sine of 140 over 188. And I get phi to be about 16 degrees. We're going to round there. So if phi is 16 right here, then 50 plus 16 is 66 degrees. Sorry. So my angle is north 66 degrees east with a magnitude of 188 units. And that is the triangle method. So now we're going to do basically the same thing, but we're going to use the parallelogram method. So I'm going to redraw this and create a parallelogram. There's my north-south line, my east-west line. I know that I have 50 degrees here. Now parallelogram means I have to have tail to tail, so I'm actually going to draw my 80 down here. And my resultant is going to be a diagonal, but I have to actually I have to complete this parallelogram. I know that this is 120, this is 80, this degree measure is 50, and I know that my resultant is going to come right up through as a diagonal. And as you can see, the resultant in the triangle method is the same location and everything as it is here in the parallelogram. So once again, I know that if that is 50, then this is a complement 40. I know that this is 140. So we've already done the law of sines, and we already can say that the magnitude is 188. Now here's the difference with the parallelogram method. With this one, and you don't have to, I did do it a little differently. With this one, I actually went in and I found this angle down here by using the law of sines. I did the sine of, oh, actually, hold on, let me label this. This is also 120. So I would have this sine of alpha over 120, and that would be equal to the sine of 140. Hopefully we remember that opposite angles are congruent in a parallelogram, so that's also 140. The sine of 140 over my magnitude, which is 188. So alpha is going to be the sine inverse of all those things, and that's 24.2 degrees. A little different way of looking at it. So if I take then 90 minus 24.2, or 24, I get 66 degrees. So once again, I know that my angle is 66 degrees, my quadrant bearing. So magnitude is still 188, and I still am north 66 degrees west. Okay. So let's talk a little bit about some special cases with vector addition. When you add two opposite vectors, something can happen. It's called the null vector, or it's a zero vector. We can write this as a 0 with a little vector above it, or we can just write it as a 0. It has a magnitude of 0 and no specific direction. So if I were to add this vector with this vector, it would be, the resultant would be 0. A vector can also be multiplied by a scalar. So if we multiply a vector by a number, it has a magnitude of k times vector v. Its direction is determined by the sign of k. So if k is positive or greater than 0, it has the same direction as v. If k is negative, k times v has the opposite direction. Okay, so let's look at how that works. Find the direction and magnitude of the following vectors. So u has a magnitude of 22 and a direction of 31 degrees west of north. So here's my vector. We're going to make it 31 degrees west of north. And it has a magnitude of 22. If we want negative 3u, I'm going to multiply negative 3 times the magnitude 22. So I need a magnitude of 66, but the negative is going to make it go in the other direction. So I would go in the complete opposite direction, making it 3 times as long. And this has a magnitude of 66. Now, the direction angle, if we're doing quadrant bearing, this is a vertical angle to the north line here. So that's also 31, but it would be 31 degrees east of south with a magnitude of 66. Okay, and lastly, letter B. If V has a magnitude of 48 and a direction of 0, 42 degrees, find 3/4 V. So we have a true bearing. There's my north line. 42 degrees might be here. And it has a magnitude of 48. So if I want 3/4 of that, I would take 3/4 of 48, which is 36. And if it's going in the same direction, it's going to be right on the same line. So maybe here, the same vector, same direction, only the magnitude is 38. Okay, and that takes up us up through 8.1. Lots of information there.